All right, cough just in time for it to start recording. All right, we'll make a start. As usual, this is more for the people listening at home. We have our class test Friday in 2 days' time, and that's what you can see in the bottom of the slide there. So the class test opens at 8, closes at at midnight. You have about an hour to do it. If you have any questions about it or need extensions, or if you've had a reasonable adjustment plan and haven't sent that to David, do that ASAP. But yeah, there'll always be one person who didn't know about the class test, so that's why I remind every lecture, tutorial and lab. There's a mock test as well that you can use to practice uploading. Someone mentioned that it only allowed 2 attempts, so I've changed that. It allows multiple attempts so that you can keep practicing to make sure that you can get great marks for the class test. I think that's it really. Someone was asking about where we can get some more information about laboratories. If you click on the link for each week's module, you'll get sent to a page that gives you an overview. You can click on this link here that will send you to more resources. And this is the content that we have if someone has to submit it online because they have COVID or something similar. But what you'll notice is that it has a video. And the videos only go for about 10 minutes, but it actually goes through what you're going to do in the lab. So it's nice preparation. Put it on 2 times like you do with the lectures, have a watch, and you'll be all prepared for the laboratory. All right, that's that one. Get started on the lecture. So Monday's lecture was a bit more brief and just to cover some of the stuff you might already know, such as Newton's first, second and third law. Today it's going to be a lot more problems that I'm going to work through with you. We're going to look at how we can use Newton's first law to solve problems, then Newton's second law, so when something's in motion, and then I'm going to start to add different elements. So initially we're going to look at horizontal forces, pushing boxes, then we're going to look at vertical boxes, and then slowly an incline, and then we're going to add friction, and soon we'll do it all stepwise, so that way you can follow the new ways to solve it. All right, so that's what we're going to cover. Newton's first law first to solve problems, Newton's second law second to solve problems, and then we're going to have a look at how friction can play a role. I did have a demo, but I probably wouldn't have had time to do it to show friction, but I couldn't get it to work in time. So just to remember, very briefly, the 4 common forces that we were looking at was that contact force, where, for example, we have the normal force pointing up perpendicular to the surface, and you'll notice that this will be perpendicular even if it's on an incline. So that's one important one to remember for that vector for the normal force. You have the tension force, and that goes up the string, which is inelastic. We don't have elasticity in our strings for this course. You have the weight force, which is straight towards the ground, to the centre of the earth, so that's down. So for example, if you had something on an incline, that weight force, or force G, is going to be down, and then the normal force is going to be on an angle perpendicular to the incline. And so it's these types of vectors that I want you to start picturing and knowing which ones you have to separate into the x and y coordinates. And of course we have a contact force. This will be the last one that we're going to look at in today's lecture, and that's friction. So if the box is getting pushed in this direction, it's going to have the friction force in the opposite direction because it's going to be trying to hinder the movement. And there's 2 different types of friction forces. We've got one called static friction, static friction, and then we got kinetic friction. Static being when it's not in motion, so if I try to move this bottle with a little bit of force, it's not going to move. But then if I push hard enough, it will start to move. It's rubber, so it takes a lot of force. And then that will be kinetic friction. So we'll have a look at those 2. But we're going to first look at something that's not moving and doesn't have any friction to worry about initially. And that's when we have the net force is all equal to 0. They all cancel out. There's no motion of the object or the box. So the way that we're going to look at that is we're going to draw a free body diagram, similar with the vectors that I showed on the previous slide with all the different forces, and then we're going to separate each one into the x and y coordinates. And to start with, this will be pretty easy because we'll only have force vectors up or horizontal, but when you start to look at inclines and stuff, then it might get a little bit more harder. Not much, nothing that you can't cope with. So to do this, we're going to identify the relevant problem. This is, for example, we have a box sitting on a table. It's got no motion, so we're going to use Newton's first law because the net force is all equal to 0. We're going to draw the free body diagram. And the reason why I'm going to say this in particular is because it's an easy 2-mark question in an exam. So if you get that wrong, then you lose marks. So it's really important to be able to draw that because that helps to then solve the problem. And it'll be obvious once we start to do that. So you're going to draw the physical situation, a box on a table. And then you're going to establish that it's at equilibrium. So when I say equilibrium, it's relaxed. That means there's no motion, and all the net force is equal to 0. And then you're going to draw the vectors as part of your free body diagram. And the 5th part of the setup is to identify the coordinates. So this is where you identify where the positive y-axis is and the positive x-axis. So typically, I'll have positive up for the y and then positive x across the page, usually, but you don't have to. You can have them in opposite directions. It'll give you the same answer. All right, so once you've done your free body diagram, you've identified the vectors and the x and y coordinates, then you can start executing. And this is where we look at the object. There might be more than one object, but you start with one. You identify all the force vectors that sum up to 0 for both x and y. And then you evaluate. So usually you're asked to find something, and we'll look at some different examples. So the second way to solve it is if it's a dynamic problem where the box is moving. You're pushing it across the table, you have a force vector going across, you might have friction force, which we'll see later on. You'll still have the normal force going perpendicular from the table and the weight force going down, but you might be asked to solve for the acceleration of the box as it's pushed with a constant force. For this example, we know that the sum of the forces will equal to the mass times acceleration. So you will tend to need to put in all the net forces for that on this side, for the x and the y, and then solve. And we use a similar strategy. We identify that it's moving, we need Newton's second law, then we draw the free body diagram. This one, we need to draw the vectors and also identify the x, y coordinates. So it's exactly the same. The only thing that's different is instead of the net forces equaling 0, it's equaling mass times acceleration. Once you've done your free body diagram, you execute. For example, you try and remove any unknowns and try and find an expression, for example, for acceleration, if that's what the question asks. The opposite is if you know the acceleration and you might need to find one of the forces, for example, acting on the box to get it to move to that acceleration. So, is there anything I've missed there? Nope. All right, so we're going to have a look at an example. Like I said, this is going to be a lot more of me showing you how to solve a problem rather than identifying new concepts, because we've identified all the concepts. Now we're going to look at how we can solve. So I'm going to start with just x movement, but with that we both have y and x coordinates. So once this starts up, I'll get it all sorted. So the first thing we're going to do for this one, so I've got two boxes. We're not going to look at friction just yet. We'll look at that later. But when we do incorporate friction, it's just going to be adding that component into these equations. So it won't be a completely new problem solving strategy. All right, so we've got a non-stretchy cord. The first box has a mass of 10 kilograms. The second box has a mass of 12 kilograms. And so we have a cord that's attached to both of them. So if we were to draw that setup, this is my mass 2, mass 1, and our cord, and it's on a surface. All right, so I'm going to label 2 and 1. All right, doesn't matter which one's 1 as long as it's consistent with your symbols later on. So the first box is 10 kilograms. I'm just going to put that here. And the second one is 12. So we've got our problem there. Now we need to start drawing the rest of the free body diagram. So for example, we'll have a normal force here, and I'm going to put 2 to represent the normal force of the second box. And we're going to have a normal force 1 for the first box. You could do one at a time. Let me stop that from auto-focusing. That should be better. All right, so let's just focus on this one from now on. So we have the weight force, which also equals to the force due to gravity, which also equals ma. Same here. Sorry, that's, yep, G, sorry, mg. And we have the same for this one as well. There we go. So we've got acceleration due to gravity and the mass of the box, which we know. So we can actually calculate that. But we'll get to that in a moment. And then we also have this tension force. Now we know from Newton's third law that this tension force is going to be equal to this tension force. And that's because they have to be equal and opposite. And then we're given a force that it's moving across the table. And so this force here is equal to 40 newtons. Yep, my handwriting's atrocious, but that's all right. All right, so we have the free body diagram almost complete. There's one thing I haven't identified, and that is that I want positive y up and positive x across. Like I said, I typically go that way, but not always, but most of the time. So now I'm going to look at the first box, so the box that weighs 10 kilograms, and I'm going to look at the net forces for the x and the y direction. So box 1, we're going to look y first, and I'm going to say that we have the net force y is equal to MAY. But the thing is, I know that my box isn't moving up and down. So we're going to apply Newton's first law. So I'm going to say that this is equal to 0, because it is. And we can identify the net forces. So we have a positive normal force up minus the weight force down. So that's my net force. So normal force minus Fg1, whichever symbol you want to put in. In fact, I'm going to put in, because we know the mass, I'm going to put in mg, and that is equal to 0. So I can actually get a term for the normal force, which I might not know. So the normal force 1 for box 1 is equal to mg, if I rearrange that equation. So that's not too bad, and probably I won't even need that equation, but I need you to know how to do this just in case you do. So if we look at the x direction now for box 1, we can do the same thing. So the sum of the forces, x, is equal to mass times acceleration. I'm going to remember to put my symbols in for when I combine them. So for this one, the x acceleration is in the x direction, so I'll put the x there. So what we have here is the tension force, and I'm going to put a P here to represent pulling, and the pulling force. So this one's in the opposite, in the positive x direction. So we have Fp minus the tension force, which is in the opposite direction, negative x. It's pretty straightforward right now. Yeah? Because I still get to mark in exams sometimes, and people will get to this a question like this, and they'll simply write F equals ma. So I want to make sure that I don't get that this year. All right, so once we've got those identified, we can start looking at the second box. So box 2 is going to be very similar, except for we don't have the pulling force. So if we look at the vectors, we only have the normal force up, the weight force down, and the tension force across. So we can write that out, very similar. So you can basically copy for the normal net force in the y direction. So this one's going to be the normal force 2 minus mass 2g equals 0. And then we can get an expression for the normal force of box 2, which is equal to m2g. And it makes sense, right? Because they should be equal and opposite. And then we can have a look at the x coordinates, and this one's going to be a little bit simpler because we only have one force in that direction. All right, and with this one, we know that the acceleration x of box 2 is going to be equal to the acceleration of box 1. So we're going to find an expression for that. And we've got Ft is now equal to mass 2 acceleration A, because we've only got that one force vector for that box. So once we have that, we can solve for our equation and try and get rid of any unknowns. So the two equations that I'm going to look at is this one here. Is that blurry? Yeah, sorry. You're just going to have to... It must unfocus when I move it around. All right, so we're going to look at this equation here, and we're going to have a look at this equation here. And what we're going to do is get rid of the unknowns, for example, the tension force. So we know that the tension force Ft is equal to mass 2 times acceleration A. So we can substitute that into our equation, and we get an expression for Fp. So if we do that, so I'm going to write, let's do equation 1, equation 2. So equation 1 plus equation 2, we get Fp from here. And then once you rearrange that, we can get M1AX plus M2AX. And what you'll notice is that eventually we can isolate the accelerations out of that. So if we did that, it would be AX M1 plus M2. So now we have an isolated acceleration term that we can rearrange. Because you remember, we already know what the pulling force is. It was given in the question. We know the mass 1 and the mass 2. So now we have an expression for acceleration, which is going to be Fp minus the sum of the masses. And we can solve. So once you do that, you get 40 newtons, 10 plus 12. So it should be almost 2 meters per second, just under 2 meters per second for acceleration. And then you can sub that back into one of the terms for Ft to find Ft. So we know Ft is equal to Ft is equal to mass 2 times acceleration. So if we know that the mass 2 is 12 kilograms and roughly the acceleration is equal to 2 meters per second, we can solve for the tension force as well. Okay, so that's a very, I wanted to break that down a lot. The solution is on the slides as well, so you don't need to worry about writing this down. And it has the full calculations. I just didn't use my calculator. But yeah, I really wanted to break that down and make it obvious about how to do it. But is there any questions while we go back to the slides? So we got the free body diagram. We got the box 1, y direction and x direction. Then we isolate box 2, y, x, doesn't matter which one you do first. And then you try and get rid of the unknowns. Typically it is trying to get rid of the tension force. So we usually do that. So this is the expression that we got for acceleration, where we have the pulling force and the sum of the masses, and it's just under 2 meters per second. And then you sub back into Ft. Now for those at home, I have the animation video to go through it as well. We're not going to show it here because I just went through it. So we looked at the x direction. I can't see any questions, which is good. We're going to look at the upward machine. Basically, this is two masses on a pulley system that move up and down, depending on which one's heavier. So you can see that I've drawn I haven't drawn a diagram. I'll put a diagram in. Now to start with, for this week only, we're not going to consider the pulley. But once we start looking at torque and rotational motion of a cylinder, for example, so we're going to simplify this as a cylinder, that's going to be in week 4 of the mechanics section. We'll include the torque of the pulley as well. But to begin with, we're just going to start with a simple non-existent pulley system. So for this one, we have mass 1 and mass 2. And it's sort of obviously saying that mass 1 is larger in weight than mass 2. So we're going to get acceleration up for mass 2 and acceleration down for mass 1. So this is where we have no x net force to worry about, just the y. So I won't go through this one because I want to make sure we've got enough time for the rest of them as well. But I've got the solution here. So for this one, we look at mass 1, the big mass. So this is a free body diagram I've drawn. You don't have to draw the entire setup. I've got the free body diagram and the vectors drawn for mass 1, where we have the tension force on the string going up. and the weight force going down again, where it's equal to mass 1, being mass 1 here, times G, and I've identified as Y being positive up. Again, you could have it positive down, but that's what I've picked for this one. For the second mass, we have the tension force going up, and it's equal to the tension force here, and the weight force going down. So it's important to note that when we have to include the pulley, those tension forces will not be equal. It will be FT1 and FT2. So just important to remember for that. So again, we can write some of the forces in the Y direction. We know there's some sort of acceleration, so we're going to use the second law, Newton's second law, and we can write the sum of the forces. They're going to be very similar. There's just going to be a change in signs. So for mass 1, tension force is positive up with the direction that we've identified as positive, minus the Fg, or mass times G, and that's equal to minus mass times acceleration, because the acceleration for that object is down. Second object has a tension force up, so it's positive, minus mass 2G for the weight force. This acceleration, that little one's going up, so we have no negative sign, it's positive, mass 2 times acceleration. So I find this one even simpler than the previous example, because you don't have to worry about any X component whatsoever, and they're very similar as long as you get those signs correct. Okay, so we have to solve that equation, and we're going to remove the tension forces. So again, that's usually the unknown that we have in our systems. So for this one, we have equation 1 and equation 2, and with equation 2, I'm going to minus the first equation to get rid of that tension force. So basically, we've got tension force here minus this tension force, and we're going to sub it into the equation. So if we have that, we have minus m2g from this equation, and that's going to be plus m1g because it's minus minus. It equals to m2a from this side of the equation, and then again minus minus gives us a plus for the m1a1. So now we can isolate both the g's again, so we can put minus mass 2 plus mass 1 in brackets and put g outside because it's constant. And again, we can do that with the acceleration, put that outside the brackets, and we have mass 2 plus m1 inside the brackets. This allows us to rearrange the equation, so mass 2 plus mass 1, divide that by both sides, and we get this expression for acceleration. And from there, we can substitute that back into the expression for 1, and we can get a term that we can find for Ft, or the tension force. So you might only be asked to find the acceleration and not the tension, or vice versa. But yeah, so that's how you would solve it. And then once we start to look at the pulley as well, we add an additional component to that. And that will be in a couple of weeks' time. So we've done X motion or dynamics. We looked at the upward, which is like an elevator type thing, where we only have the Y component. What about if we do have that incline? So if we have a frictionless incline, again, we'll add friction at the end. But we've got, for example, I don't know why it looks like a letter. It's a parcel, sorry, it's a parcel. But yeah, we've got a parcel on an incline, and it's probably sliding down because it's got no friction. So the first thing we want to do is, now that we've identified what the situation is using this diagram, we can start to look at the free body diagram. So for that one, it's a little bit more complicated, but not too complicated. We've got the normal force perpendicular from the surface. We have the weight force going down. So depending on what way you've identified as the positive Y and the positive X will determine which force vector you will separate out into the X and Y components. So for this one, which I typically do, I will go positive X down the incline, and I think it's just because it's easier to solve. You'll still get the right answer even if you tilt those axes. So we've got positive X down the incline, positive Y in the direction of the normal force, or perpendicular from the surface, and then the Fg we can separate out into the X component for the force G, or weight force, and then the Y. Similar to what we do with the initial velocity, like we've done in the laboratory, like we've done in the tutorial, or will do in the tutorial. We'll separate them out using the force G, or mass times G sine theta for the x-axis, and mg cos theta for the y. So that's how you separate them out. And all we're doing now is when we find the net force of our object, we use those terms in place for the y and x respectively. So for the y direction, we have the force of the y, the sum of the forces in the y direction is equal to the mass times acceleration. We know there's no movement of the box in that direction, so we're using Newton's first law, which is equal to 0. We have a positive normal force minus the mg cos theta, so this FGY force that we've identified here as mg cos theta, and that's all equal to 0. Rearrange to get our normal force term that we could probably substitute in a bit. So once we have that, we have an x direction which is similar, but we have acceleration, so we're using Newton's second law. With this one, we only have the weight force going down the axes or down the incline. So this one is mg sine theta because it's going in the positive x direction, equal to mass times acceleration. With that scenario, we can easily remove the masses, they cancel out, and we have an expression for acceleration already. When it starts to get difficult is when we have some string going up here to a pulley and another box hanging down. And then we have to worry about two objects, similar to what we've done in the previous examples. But we'll get to that. It's not impossible for sure. But before we do that, we do know that most objects will have some sort of associated friction. So let's look at how we can associate that to our problems. So if we have this box sliding down, like I mentioned before, we'll have a frictional force vector going in the opposite direction. So it's similar to how caterpillars move. They will not move. I was just looking at the title. I might change that. But yeah, so caterpillars won't move unless they have some sort of friction between the legs or their feet on the object. So the friction between their feet of the caterpillar on the surface is what allows them to walk. And so we're going to make sure that we incorporate that very important part of movement before we continue on to tomorrow's lecture. All right, so when we have a body at rest or sliding on a surface, the frictional force is parallel to that surface, but in the opposite direction. So we've identified that already. So if we have the push or pull across the page, the frictional force is going to be in the opposite direction. But like I mentioned, there's two different types of frictional forces that we're going to come across. But they're easy to identify, and they have very similar equations and coefficients. So if we have a look at the interface between an object and the surface, the frictional force is just based on the interactions that occur at the molecular level as well as the physical properties of the surface. So for example, the rubber on my bottle is going to have a higher frictional coefficient and it's going to be harder to push across the surface than the glass itself because they have different properties. When it's in motion or when it's not in motion, we have two different forces. So the motion is kinetic, meaning it's moving. The static, meaning not moving, is the static friction. But we have two different equations. So this mu, k, represents the kinetic coefficient of an object. You'll be given that, or you might be asked to find that. It's not something that you need to remember. You just need to know the difference between mu k and mu s. So for this kinetic friction force, when we start to look at incorporating this into our sum of the sum of the forces, this is the equation we're going to look at. So where n is the normal force, Fn or little n, depending on what textbook you read. So with the static friction, it acts when there's no motion. So it's just before it starts to move. So I've got some force on here, but my bottle's not moving. So that's when we use the static friction. And that's going to be equal to mu s times the normal force. So the static friction coefficient times the normal force. So the static friction force can vary between 0 and a maximum value. And I've got a graph that represents that. And we've got each step to show how we can sort of plot or visualize the friction that's going on, because it is a little bit different. It's not a linear relationship like you might think. So if we have a box stationary, there's no friction force because there's no force pulling in the X component or along that axis. So no applied force, box is at rest, no friction. The frictional force is equal to 0. You don't need to worry about it. But once you start to pull, there is some sort of associated frictional force, and it's going to be less than the static coefficient times the normal force. So this is our tension force, and we have that small static friction vector going in the opposite direction. So once we start applying a stronger tension force to try and get that box to move, the frictional force will then be equal to the static coefficient times the normal force. And then once it does start moving, you have the kinetic frictional force, so it just changes from Fs to Fk, and that's equal to the static coefficient times the normal force. And so what I was going to do is demonstrate this and show you how it plots, but instead I've just got a static plot, pun intended. All right, so we have this sort of relationship here. So initially, when we have the static friction coefficient going on, we have this linear relationship. It moves up to a force, so you can see the force on the y-axis and the tension force on the x-axis. So once you move up, we have this sort of linear relationship between the two forces. You'll notice that you actually need a higher force for the frictional force before it starts to move. And you can think of windscreen wipers. Sometimes they get stuck. They need a bit more extra force to kick them across your window, depending how dirty it is. And that applies to any friction that you have. So once it reaches the force that it's required to move the object, then we have almost constant relationship with the force, this kinetic force friction here. So it's just almost, it's plateaued, that's the word I'm looking for. So that's the sort of relationship, and that's why we have the two equations. So when it's in this area, we use the static friction coefficient times the normal force. When it's in this area, we use the kinetic friction coefficient. So we can have a look at how they vary. So we have these two, I'm not going to go through all of them, just the obvious ones. So we have the coefficient of static friction and the coefficient of kinetic friction. And we can see that with rubber on concrete, for example, it's quite high, but Teflon, like you use for the non-stick pans, will be really low. And so you'll usually be given those values. Like I mentioned, you do not need to remember them, but you should know what type of, what the coefficients mean in terms on how sticky the object might be. All right, I've given that example already, but just in case for the people who aren't listening to my lecture, the static friction example is similar to the windscreen wipers, so it'll get stuck, and that's the squeak that sometimes you hear. So there's one more force that we have not covered, and someone asked me in the laboratory yesterday, I can't remember if it was the morning or afternoon, and so that's this one. So we're going to go on to the last concept before we look at some more examples until we run out of time, basically. One thing we haven't looked at yet is drag. Drag is a dominant factor in many sporting events. You've got swimming, running, all of the things that you need speed for. In swimming, it's the reason why people will shave their body hair or they wear the bodysuits. In cycling, it's the reason why one sees a peloton or a line of riders. In PHYS1210, we won't use drag much in our calculations or problem solvings, but it's still important to know how it's calculated. You may be surprised to know that the frictional force is independent of the velocity and the area. For objects moving through gases or fluids, this is not true. The resistive force is called drag, and the full calculation of drag is quite complicated. For this reason, we have a good approximation, which is represented here. This is only for low speeds in viscous fluids or small objects in air, where we have B, which is the constant which is dependent on the viscosity, and V, which is the velocity. Something else that you will notice from this equation is that it's negative.
which means that the force due to the drag is in the opposite direction to the velocity. For objects moving at high speeds, such as aeroplanes, cars or cricket balls, this is the equation used to calculate the drag force. So you can see some different variables here, such as CD, which is a constant, rho, which is the density, and A, which is the area. But the main takeaway here is that the force is proportional to velocity squared.
All right, so that's the summary that just went through in the animation. So we have two different equations we can use for the drag force. We don't really do too much in this course, but there is a question in it in the tutorial next week, and that's basically the extent of what we do for this subject. If you go on to second year physics, then you'll start to do some more stuff with David. I believe he's teaching it. But yeah, this is all we need to remember for now. So this B is the coefficient of air resistance. So obviously we always have these coefficients. And I think this is a similar example that we're going to use in the tutorial next week where we try and find B. I can't really remember. So I've only done it a few times. But anyway, and the other one is where we got movement at higher speeds, aeroplanes, cars, cricket balls, and that's where we have this force which is proportional to the velocity squared. So they're the two equations that you would need to look at. So we can have a look at the CD, or the drag coefficient, and how that relates. So we got the drag coefficient, we got rho, the area, and this is density, sorry, rho is equal to density, and area, and then velocity squared. So that sort of makes sense. When we've got some drag, it will depend on how dense the material is for example, air. If it's more moist, it's probably going to be higher density, and then also the area of the object as well. So let's have a look at some of the drag coefficients for various objects. So we've got a human upright position or a human running, and you can see the drag coefficient will change. We've also got a penguin, pretty low drag coefficient. So it all depends on not only the area of the object, but also the material. For example, the penguin will have the slippery feathers or whatever. All right, so they're the sort of drag coefficients. Again, nothing that you need to remember, just knowing when you have a high drag coefficient compared to a low drag coefficient, what that sort of represents for the force due to drag. So we have just over 10 minutes, and I'm going to see how many examples we can go through. I do have all the solutions for these available on Canvas, so that's fine as well, but they're more quicker, whereas here you can ask me if there's any questions about the maths or anything like that. So we have two boxes. They're connected to a lightweight inelastic string as shown, and we've been given the kinetic friction coefficient as 0.2. So we're going to find the acceleration of the system. We don't even need to worry about the static setup because it's already in motion, or it will be. We're not going to consider the pulley just yet, but we will in week 4 of our stuff. So object 1 has 5 kilograms, and object 2 is 2 kilograms. So you're going to draw those objects. For each object, identify the forces, define the XY coordinates, and then solve for the various ones. So we can do that. I'm just seeing which one would probably be most beneficial. I think we'll just go with this one, and then we'll see how much time. Like I said, there's more examples available in the lecture notes as well. So let's do that. Once it's up, it's about 10 minutes slow. All right, so we'll do that example. So I've just started while that drag video was on. Just trying to get there. I'm just trying to stop it from playing the video in the background. All right, so we have our mass 1, and let's zoom in to make sure that it's nice and good. All right, and then mass 2. So we can identify the forces. We have the normal force 1 for box 1, and then Fg going down for box 1. We can write that as M1G. And again, this one's a lot, I should say, tension force as well. So that's all we've got, as well as the friction force now. So that's how we'd write it, by including that one concept that we've just introduced. So this is going to be kinetic friction force, and we already know that that's equal to mu k times the normal force, which is the same here. So we've got that. Now we can introduce the force vectors for object 2. So we've only got the 4 here. Object 2 only has 2 in the y direction. The tension force, which is going to be equal to this tension force until we start to introduce the pulley system. And then we have Fg2, which is equal to mass 2g. So you can already see that we can start to identify the forces in the x and y direction for box 1, but just the y direction for box 2. So I might as well do that now, because it looks like the path of least resistance. So for this one, we have some sort of acceleration of the system. One thing I've forgotten is the x and y. So I'm going to put a little negative sign to represent the negative direction for that one. And so we've got the tension force up minus the m2g for the force due to gravity on the box, and then minus mass 1 times acceleration a. Okay, and so that's box 2 done. I need some different colours, but this one doesn't have different colours. So we can have a look at box 1 now. So we can have a look at the sum of the forces in the x direction, which equals to max, where mass is mass 1, not mass 2, and the acceleration is the same as the acceleration here. And I just realised that this is, because I'm used to the previous example. So we got the acceleration, and I don't even think we don't even need to worry about saying it's y, but for now. All right, so we have the sum of the forces, and that's going to be Ft in the positive direction minus the friction force, and I'm going to substitute this right in straight away because we've just identified that equation, and we've got mass 1 times acceleration. We can do the same in the y. This one is going to be equal to 0 because because it's got no motion up and down, and so we've just got, oops, where did my solution go? There we go. So we have the normal force in the positive y minus the mass 1 g equals 0. So if you got up to this step in an exam, you'd get most of your marks correct. You'd get at least half of them. But I think people get stuck on this and then just don't move on. So it's really important to be able to identify those force vectors and apply them like this. So once we have some of our, once we've identified all those, we can start figuring out which are our unknowns. For example, the tension force is unknown, and we can look at how we can substitute that in. So with that, I'm just trying to see what I've done here differently. No, it looks okay. So we can find an expression for the normal force, for example, here. So normal force is going to be equal to minus m1g. And so we can actually put that into the equation up here for the normal force, because we don't know that one. So with that, we can put in, we can substitute. I'm going to put an arrow down here. So now we have Ft minus mu k, and then we have our, that shouldn't be a negative, m1g, which is our normal force, and that's equal to m1a. And so we can get some different, we can look at that and we can incorporate that into the previous examples to get rid of tension force and then find an expression for acceleration. So I might stop that part there because we've only got 5 more minutes, but I'll show you how I've got the acceleration equation. If I go back to the computer, it'll probably be easier to read anyway because it's not my handwriting. And it's not going to work. My fingers aren't even cold, so it should work. Looks like the system's frozen. All right, that hasn't happened before. First time for everything. Now, I can't turn it on and off. Yeah, it's completely frozen. All right, well, that's a bit sad. All right, so we'll have to keep going on the tablet for a couple of minutes, but what we're going to do, I'll show you the expression you should get for acceleration. Awesome. There it is. Okay. Yep, so we have it back to working. So what you should get is an expression for acceleration which is very similar to this. So you can see that we've got the expression we obtained for the friction force. So that's what we've added to the problem. And we can rearrange the equation and we get mass 1g minus mu k, which we know mass 2 and we know g, and then we also know the sums of the masses. So what we're able to do is we're able to get rid of the tension force that we didn't know, like we did previously, and find the expression for acceleration that we have all the terms for. So I'll leave that up there. There's two other examples that I can see. We've got this one here, inclined plane with friction. So this is with a skier. So it's going to be doing a similar example where we have the incline, but we're going to add the friction coefficient to it. And then we have one where we have an angle incline, like here. And then we have the hanging weight. This is the standard that I would expect people to know how to do at the end of this lecture series. And not only that, incorporate the pulley at the end of week 4. All right, well, it looks like everyone's leaving early, so we'll end it there. But I've got all those worked out solutions available on Canvas on the page, and I'll put those up now just so you know where they are. If you've got any questions, you can come up and ask me. I always think that people will do well, and then I get to the exam and it's a bit of a struggle. So we've got lecture 2. The lecture 2 page here has all the different examples that we go through. So you can have a look there at how they're solved. All right. Leave it there. Come ask me if you've got any questions. Otherwise, I'll see you in tomorrow's lecture. It's always a good sign.